Hey math fans, Alex here. In this last section of chapter 4, we're going to talk about variance a little bit more, some properties, then we're going to end with the correlation coefficient, which you might remember from anything that you read about in linear regression or statistics for psychology. Okay, so first let's recall what the variance is. The variance of a random variable x is just the expected value of the squares of that random variable minus the mean. Okay, so again, just a little reminder that the mean of x is the same thing as the expectation value of x, and I just use this notation because it's more convenient and less of a hassle to write. But we proved that another formulation of variance, a more useful way to formulate it, is that it's the expectation value of the distribution x squared minus the expected value of x quantities squared. Okay, because those we can easily find using integration, and then just plug it in. So a couple of really important properties of variance. Number one, the variance of the random variable 1 is equal to 0, where I'm just going to remind you the random variable 1 is just that which is equal to 1 with probability 100%. Okay, so it makes sense, right, that if it's only equal to 1, the distance between 1 and the mean, which has to be 1, is 0. If you square that a bunch of times, you're still going to get 0. And if you add up the results, you're going to get 0. So it makes sense why the variance of 1 is equal to 0. The variance of a constant times the random variable. Well, remember with expectation, you just pulled the constant out. With variance, you can do the same, but it's going to be that constant squared. And then third, for x and y independent random variables, and yes, this is pretty important, the variance of the sum is equal to the sum of the variances. All right, let's go ahead and prove that. Okay, so I'm going to go ahead and leave 1 and 2 as an exercise for you. It's really not that bad. Just figure out what the expectation value is, and then square it, and then figure out the expectation value of that, and it should be pretty straightforward. So we're going to spend some time to prove 3. So for 3, just for convenience sake, we're going to go ahead and let the expectation value of x be just the mean of x, and the expectation of y is just going to be the mean of y. Okay, so by definition, the variance of the sum is going to be the expected value of x plus y squared minus the expected value of x plus y, and then this quantity is squared. Okay, but remember how it worked for expectation values. First thing I'm going to go ahead and do is I'm going to fill in the parentheses. So this is x squared plus 2xy plus y squared minus, and then remember this is just going to be the expectation value of x plus the expectation value of y, and we're squaring that. Okay, and this is where now I'm going to go ahead and replace this with mu sub x and mu sub y. Okay, so this is going to be the expectation of x squared plus the expectation value of 2xy plus the expectation value of y squared minus the, well, just put it in parentheses. Right, so mu sub x plus mu sub y squared. Okay, but we know how this game goes. We can pull this 2 out just without doing anything. So we get the expectation of x squared plus 2 times the expected value of xy plus the expected value of y squared minus, and then we're just going to FOIL this out. We're going to get mu sub x squared minus 2 mu sub x mu sub y plus mu sub y squared. Now, this is where that assumption about independence really comes in handy. So this is going to be the expected value of x squared plus, and then let's see, this is going to be equal 2 times, well, this is the expected value of x times the expected value of y, which I'm going to, of course, just write as mu sub x times mu sub y, plus the expected value of y squared, okay, minus mu sub x squared plus 2 mu sub x mu sub y minus mu sub y squared. Okay, so then these terms just cancel. And now rearranging, I'm going to get that this is going to equal mu sub x squared minus this quantity squared, which I'm going to actually just rewrite now as mu, or the expected value of x squared, plus the expected value of y squared minus the expected value of y all squared, because that's what this is. Okay, but we know that this is just the variance of x. We know that this is the variance of y, and we're done. Okay, so one question that we might want to ask ourselves, and this is a very, very useful question that is important in all fields of science and really anything that applies science. And the question is, if I'm given random variables not necessarily independent, in fact, definitely not independent, random variables x and y, the question is, can we relate them using some kind of linear model? Okay, so here's kind of the situation. Let's go ahead and let this be kind of the random variable x and the random variable y. And we have a bunch of data, right? So the random variable x takes on all these values, and if that takes on values, then maybe y takes on some values as well. Okay, so maybe there's a connection here, and there are going to be all these points. Okay, so the question that we might want to ask ourselves is, can we use a line to kind of approximate what's happening with all these points? Okay. And the answer is yes. To put it very simply, the better question is, how well is that line going to actually approximate the data? And the second decent question to ask is, how do we find the best line that goes through the data? Okay, okay, that's actually terrible writing. But some additional concerns. One, how well does the line fit the data? And question two, and what we're going to concern ourselves with now, is how to pick the best line, which is also called the line of best fit. Line of best fit. So is there some kind of way to do that? And the answer is yeah, there are actually a couple of good ways. But we're going to go ahead and imagine, right, that I can go ahead and fit a line, and the line isn't necessarily going to go through the most points. The line is going to be closest to the most points. Okay, so it might look a little something like, like that. Okay, now, how do we pick that exact line that so-called approximates the data the best? Well, it's going to be a very geometric approach that I take. And the geometric approach that I and most people commonly take is, you'll notice that for all of these values, we can drop down a vertical line that represents the distance between this point and the line itself. That's called a residual. Okay, so we can go and just do that for all these lines. And then geometrically, this line segment can be interpreted as the side length of a square that we can draw from said point. So I'm going to go ahead and do that. So we drop that line down, and I'm going to go ahead and form a square from that. Then I drop that line down, and then I get a square with perhaps a bigger area. Then we do the same thing with that residual, and then this one, is maybe just like a little stub of a square. Okay, so then the idea of linear regression is that all of these areas can be computed if you have the data, which we assume that we do. And so the answer to the question, very simply, answer, we want to minimize the sums of the squares of the residuals. Okay, and I should probably, define a residual, so I'll just kind of give you an example. Okay, so that's an example of a residual. And if you square it, you get the area of a square. All right, so let's see if we can mathematically figure out how to answer the question. So how can we minimize the sums of the squares of the residuals to produce a line that fits the data the best? Well, the first thing that we should maybe do is suppose the line has the form, what? Y equals mx plus b? Kinda. We're going to assume that it's going to take on the form y is equal to c1 hat x plus c0 hat, okay, where c1 hat and c0 hat are parameters, and they're parameters that we're trying to find, to be determined. Okay, so in order to answer the question, we're trying to minimize the sums of the squares of the residuals. So it might help to figure out what a residual actually is. So I went ahead and plotted it for you. So for this residual right here, I went ahead and kind of magnified it a little bit, and you'll notice that there are 2 points to the residual. There's the point that's actually on the line, which we're going to call c1 hat x sub I plus c0 hat, where x sub I is the x-coordinate of the data, and then we just plugged it into the supposed line. Okay, and this point right here is the actual, point, and it's the y-coordinate of that point. So if this is x sub I, then the actual data point is going to be at y sub I. Okay, so we have that this point up here is c1 hat xi plus c0 hat, and this point is just yi. And since we're going to be squaring things, it really doesn't matter what order these are in, so I'm going to choose to put the y sub I first. Okay, so in order to minimize the sums of the squares of the residuals, we note that the residual is really going to be something like, y sub I minus, and then c1 hat x sub I plus c0 hat, right? So that's kind of step 1, is figuring out what that residual is. Step 2, we're going to square the residual. Okay, so all we're going to do is just take this quantity and square it. Okay, and in this instance, I'm going to go ahead and distribute the minus sign. So this is going to be minus a c1 hat xi minus a c0 hat square. But remember, we want to minimize all of the sums of the squares. So sums of squares of the residuals, well, that's going to be summing over all data, which we're just going to assume it's I, of this quantity y sub I minus c1 hat xi minus c0 hat, all squared. We want to try to then minimize that. So that's kind of the last step. Well, how are we going to minimize a quantity like this? Well, the answer is we're going to take partial derivatives. Okay, so remember in Calc 1, if you have a situation in which you have a graph and you're trying to figure out the maxes and mins, what did you do? You took the derivative of the function and set it equal to 0. And then you got all maxes and mins. Well, in more than a single variable, it's a little more complicated because you could have saddle points and whatnot, but this answer is just going to give us the minimum, so you're going to have to take my word for it. And how are we going to do that? Well, we're going to go ahead and let this quantity, we're going to assume that this is going to be just a function of the parameters c0 hat and c1 hat. We're trying to minimize that function. So the idea is going to be to set the partial derivative of f with respect to, say, c0 hat equal to 0, and the partial of f with respect to now c1 hat is equal to 0. Okay, so again, what's that going to look like? Well, that's going to be partial with respect to c0 hat of this quantity, which is going to equal 0. And we're going to have the same thing over here, partial with respect to c1 hat of this quantity is going to equal 0. Where the quantity, I'm just going to go ahead and copy and paste this. Okay, so you're not quite. Okay. Okay, let's see if we can make that just a little smaller. Okay. Sorry about the weird sizes. But let's see how we're going to do that. So, partial derivative of all this, well, first thing we're going to do is we have to apply the chain rule. Okay, and since this is a finite sum, we can go ahead and just kind of move the partial derivative inside. And then what does the chain rule say? Well, you're first taking the derivative of something to the second power. So what you're going to be doing is taking 2 times that quantity, so 2 times this sum, hat xi minus c0 hat, to the first power times the derivative of the inside. But what's the derivative of the inside? Well, everything's a constant except anything with a c0. Okay, so that means that that goes to 0, that goes to 0, and the only thing is we're going to pick up a -1. Okay, so it's going to be times a -1. Okay, and that's going to equal 0. And over here, to take the partial derivative, that's going to be, well, it's going to be the same kind of idea. It's going to be 2 times the sum, y sub I minus c1 hat xi minus c0 hat. But this time, when we look at the derivative of the inside, this still goes to 0, this still goes to 0, but now what's in front of the c1 hat? Well, it's a linear term because it's just c1 hat to the first power, and we have a negative x sub I that we need to bring out. Okay, so this is a negative x sub I term, and then all that's going to equal 0. And the last step that I'm going to do is ignore the 2 and the -1, right? Because we can just go ahead and divide that out. And then same thing here. So we can kind of divide both sides of this by -2, and we get 2 conditions. So the first condition that we get is the following. So the sum over all I of y sub I minus c1 hat x sub I minus c0 hat has to equal 0. And then the second condition, we get that the sum over I of yi minus c1 hat xi minus c0 hat times x sub I also has to equal 0. Now, the thing is, 1 and 2 form a 2x2 system of equations. for C1 hat and C0 hat respectively. Well, yeah. Now, how are we going to solve this system? I'm actually not going to do that because it's going to take a lot of work and it's kind of going to distract from the overall point. So I'm going to link a video that is extremely helpful in kind of pointing out all the details. You might need to know, so helpful note, because I never really stated this, but it might help you to remember that the mean of a random variable is the same as just maybe summing all of it like this, and then dividing by how many there are. So taking the sum of all of these values and then dividing it by n. So that might be a helpful note to kind of get you through that video. But once you do that, I'm just going to go ahead and tell you the solutions. Okay, so the solution is going to be as follows. So we're going to have that C1 hat is going to equal the sum over all I of the quantity x sub I minus mu sub x times y sub I minus mu sub y divided by the sum over all I of x sub I minus mu sub x quantity squared. And C0 hat is going to be mu sub y minus C1 hat times mu sub x. Okay, so that solves the problem. Yay, we found C1 hat, C0 hat. It looks extremely ugly and like it's practically unusable. So instead, what I'm going to do is I'm going to make a couple of substitutions to clean this up a little bit. But again, let me just reiterate what this represents. So we're trying to find the line of best fit, and lines have two parameters. It has a slope and it has the y-intercept, which we've called C1 hat and C0 hat respectively. And once you find those, you essentially have determined the line that best fits the data, that minimizes the squares formed by all of the residuals. Okay, so the way that we found that was we took this expression for all the sums of the squares of the residuals, and that's going to be a function of C0 hat and C1 hat, and we took partial derivatives and set them equal to 0 to get two conditions that gives us two equations in two unknowns. Okay, and then video is going to kind of walk you through how you solve that for C1 hat and C0 hat. And then here are the solutions. So again, looks kind of bad. So I'm going to make a couple of substitutions. Okay, so first thing is we're going to go ahead and define sigma x squared as the variance. Okay, so that's going to be the variance of the random variable x, which, remember, was the sum over all data I of x sub I minus mu sub x squared. Okay. We also are going to do the same thing for sigma y squared. Sum over all y sub I minus mu sub y squared. And just, again, as a note, I'm actually just going to put in parentheses. So sigma is called, well, it's the square root of the variance technically, but it's called the standard deviation. But again, we don't like it because it doesn't have nice properties like the variance. So in probability, we tend to work with sigma squared. Okay, and the last thing that we're going to define is we're going to define letter R as being the sum over all I, xi minus mu sub x, yi minus mu sub y, all divided by sigma x, sigma y. Okay, where R is called the correlation coefficient, for reasons that we will explore in a minute. Okay, that's very helpful to know. And with those substitutions, we can now reframe this solution set a little bit more favorably. Okay, so I encourage you to maybe write this down and pause for a minute to confirm what I'm about to write. Okay, but with these substitutions, so with these, it's clear that we get that C0 hat, well, actually, let me go back up. No, C1 hat, excuse me, is going to be, well, actually, sigma x over sigma y times C1 hat is going to equal the correlation coefficient R. And that's going to imply that C1 hat is equal to sigma y over sigma x times R. Okay, so that's C1 hat. And since C0 hat was just mu sub y minus C1 hat times mu sub x, we get that C0 hat was just mu sub y minus sigma y over sigma x r times mu sub x. Okay, so we have those coefficients now. We have the slope and the y-intercept, those two parameters that we needed. So now we can officially answer the question. So the line of best fit, which remember was y equals C1 hat x plus C0, is as follows. Y is equal to, let's see, C1 hat was sigma y over sigma x times r, and that's times x, plus C0 hat r mu sub x. This is a y. Okay? Where again, this was C1 hat, and this was C0 hat. And then rearranging things a little bit more favorably, we get the following. You know what? I'm going to write it a little differently. I'm going to write it as this. Y minus mu sub y is equal to sigma y over sigma x times r times x minus mu sub x. Okay, the reason that I wrote it like this was this is point slope form of a line, which has a really nice interpretation, and it basically states that the line of best fit goes through an ordered pair that is simply the mean of x and the mean of y, and it has this kind of odd slope, okay? But here's the thing. Linear regression says that, you know, points can do something like this, or they could do something like this. So my question to you is, slope should be positive or negative. It should have that capability, but clearly the way that this was defined as the square root of the variance, okay, so since sigma y, well, I'll just say is, you know, basically the square root of the variance of y, and likewise for the standard deviation of x. How can sigma y over sigma xr be negative? Because I want to be able to represent that. Clearly, lines can have negative slopes, so how can that be negative? Well, the only conclusion is that r has to be allowed to be negative. Okay, but we defined r. Okay, so r must be allowed to be negative. And I'm just going to recall what r was. So r was, well, let's scroll up. It's this quantity. And that makes sense, right? Because sigma x and sigma y aren't negative, right? These are square roots of things, which can't be negative. However, x sub I minus mu sub x, if this mean is fixed and you're subtracting a bunch of data, well, yeah, clearly that could be negative. And when you sum up a bunch of numbers, like that doesn't, it's not guaranteed to be positive unless you square this. Okay, so there's actually a really nice theorem that I'm going to kind of end this chapter off. It's really not in the book, but I think it should be. So we're going to go and prove this. So theorem. And the way we're going to prove that is we're going to go ahead and instead of x and y, we're going to first consider random variables a and b. And the only constraint I'm going to give you about a and b is that the expectation value of a squared and the expectation of b squared can't be 0. That's it. Well, then I'm going to go ahead and let z be some arbitrary real number. And what we're going to do is we're going to look at the random variable z times a minus b. That's a random variable in its own right. And what we can say is that, first of all, if I square this random variable, clearly that's going to be non-negative. And since a random variable is non-negative, that's going to imply that the expectation value of that random variable is also non-negative. And then we can go ahead and expand this out, can FOIL this out. So we have the expectation value of, and we're going to work with the stuff inside now, and that's going to get us z squared a squared minus 2 times the product of this and this. So 2 times ZAB plus b squared has to be non-negative. But then using properties of expectation, I can go ahead and pull out all the constants, and z is a constant. So I'm going to pull out the z squared times the expectation of a squared minus 2 times z times the expected value of ab plus just the expected value of b squared, and that has to be non-negative. Okay, and now since the above has to hold for any real number z, I didn't put any constraints on the value of z, that means that it must hold for any z that I want. So the z that we're going to choose is going to be the expected value of ab divided by the expected value of a squared, and that's why we had to put in that constraint where that couldn't be 0. Okay, so then what we get is I'm going to go ahead and see if I can just, nope, that's not what I wanted to do. Let's see if I can just copy this really quickly, make this go by a little easier, and then we have the following. Okay, so we are going to have that z squared times the expected value of a squared minus 2 times z times the expected value of AB plus the expected value of b squared, and that all has to be non-negative. Okay? And when you do that, what are you going to get? Well, you're going to get 2 expected value of a squareds, which is going to cancel out with one of these. Okay, so you're going to get the expected value of AB quantity squared divided by the expected value of just a squared. Okay, minus 2 times, and then you're going to have the expected value of AB squared. So this term is just going to repeat. Squared divided by the expected value of A squared. And then plus the expected value of B squared. It's going to be non-negative. Okay, but these are like terms. These are like terms. So what we're going to get then is that we're going to get minus one of these terms, which I'm going to go ahead and add over to this side. So then we get the expected value of b squared is going to be bigger than or equal to one of these terms, divided by the expected value of a squared. And finally, since the expected value of b squared, that's going to go ahead and be positive because b squared is positive, I can divide both sides by this expected value of b squared. Just put that on the bottom here so that we get that expected value of AB quantity squared divided by the expected value of A squared times the expected value of B squared must be less than or equal to 1. And now, again, A and B had no restrictions either, except the expectation of the square couldn't be 0. So now comes the main part. We're going to set the random variable A equal to x minus the mean of x. We're going to set B equal to y minus the mean of y. Okay, so now we get the statement that the expected value of x minus mu x times y minus mu y, and maybe all of this should be in parentheses, squared, all divided by the expected value of x minus mu x squared times the expected value of y minus mu y squared has to be less than or equal to 1. Okay, but go ahead and verify for me the definition of R. Okay, really the definition of R, if you sum all these up and you allow it to be squared, what you're going to have is that this quantity is really the same thing as R squared. And since we have that R squared is less than or equal to 1, that means that R has to be between 1 and minus 1. Okay, so what does that mean? Well, R is called the correlation coefficient. So it essentially, R gives an idea of the kind of the strength of the relationship between the random variables x and y. However, I want to point out a couple of very important things before I end this off. Number one, R is not the whole picture. Because you remember that the slope of the linear regression line, so that C1 hat, was sigma y over sigma x times R. Okay, so R kind of gives you the sign and it gives you the strength. Okay, but sigma y over sigma x gives you this magnification. Okay, so you can have a slope of 10, for instance, and this is kind of how. Maybe the standard deviation of the variable x is really small. Well, the standard deviation of the random variable y is all over the place. Okay, so that kind of plays into it as well. Okay, so that's the first thing that I wanted to point out. And the second thing to point out is that R is not always reliable. Okay, for example, if I let y be the random variable x squared, there is a set of data where the correlation coefficient R, clearly x and y are dependent on each other. But I can show you a set of data where R is equal to 0, which doesn't seem to make sense intuitively with our notion of the correlation coefficient, and that's going to be an exercise that I have you do. Okay, so that was everything on linear regression and variance. Hope this was helpful, and I will see you in the next video where we work out some solutions from chapter 4.